Hi everyone. Today I continue, as usual, solving issues, solving problems. Yesterday I solved bit manipulation problem, and I decided uh, that I will not solve them in at least in closest future. I'm at least I do not plan to solve it because it looks like a specific topic for I don't know, system engineers or something like that. And I want to solve uh, I want to solve advanced graphs topic. I learned, I read about Dijkstra's algorithm, what is prims, Kruskals. Also, there was connected topics like what is this? Union find algorithm, and union by rank, and union by also union by size of union find algorithms. So union find algorithm is basically the algorithm to group some items to subsets, and that's it. For example, we have some relations A with B, B with D. So, and A, B, and D don't have any relations with other parts of the set. So they are form subset between each other. CFI as well forms their own subset. EGJ 2's form their own subset, and H form its own subset, because even if it doesn't have any relations, it has its own it is inside its own subset. So we form to group it to these subsets. We use the technique like how to say, n items, no, how to resolve sets. Initially all elements belong to different sets. After working on given details, blah blah blah, we select member one of these members as representative, like a key of this subset. There can be many ways to select a representative. A simple one is to select with the biggest index, but we will not. If representatives, okay, we use three. Here. First of all, we create an array called parent, where ith element of the array represents ith item, and the value of the item is the index of its parent. So the ith element of the parent array is the parent of the ith element. No, here is written simple rule to identify a representative is if I is the representative of a set, then parent of I is I itself. Then we understand it, that it is representative. Also, what we make, we implement two methods. Find, first is find, second is union. Find is to find a representative of a subset. For example, let's assume that A is the representative of first subset, and we invoke find method with D as argument, and this method find should return as A. And here is its implementation. Find will return as the parent every time. So it can't be state that the parents array cannot be in the state where find will, I don't know, will be in the infinite loop invoking itself recursively. It's important because if we will have this loop, our program will be broken. So we can find the representative of every subset. Then we can union. Union is when we collect subsets. For example, let's assume we create subsets for this structure, for this example. First of all, we have no subsets, so we call it this union method with A and B. If because of there is no, sorry, maybe I am wrong. I don't know how to initiate. I don't remember how can we init this. Let's try to understand it. So we have the union method. We find parent of each item, and in the simplest case, we move subset of this item to I item. Oh no, sorry. We set parent of ith item as J's item. So if it will be A and B, we will set B. We would set B as a parent of A. and we will get the first subset as A and B. I guess we init the parents. We can init the parents array as every item is separated subset initially. So in the first example we have find will return yes. It will be guaranteed that find return something. It will return I for first item, J for second item. Yes. So we will create first subset. We will increase first subset. We will merge A and B into first subset. Then we invoke B and D. It's an if we imagine this structure as a graph, then B and D connection between or relation between B and D is an edge. It would be an edge of in this graph. So we invoke B and D. We have A and B as B in where B is representative. Then we find parent of B is B, parent of D will be D. Then we set parent of B as D. So we will reset representative of those three items to D, etc. We union all the subsets. Also, while we collect them, here is the some other ways to collect them by rank, by size, but it is not important. What is important is the fact that there can be cycles in the graph. So we need to learn. We need to know how to detect cycles and how to prevent creating cycles while we union edges into subsets. Why it is important? Because it's important because I opened this issue and this problem needs solution without cycles. So how can we prevent creating cycles? Is we can create the method isCycle. This method, okay, so let's go back. Let's make a step back. I'm hurrying. I don't need to hurry. So the union, the first union method, as we can see, is not optimal, because we each time we just change the representative to the second item. Here we don't make any checks. So how can we check it? We can we can resolve it as changing parent each time. Here we have a picture. Yeah, in our first example, it would be like something like that, but we don't need it. So we can make union by rank. The rank is we set the rank 0 for each subset initially. So here we have 4 items, and we create 4 subsets from them, and we set the rank for each of it as 0. Then we merge first 2 items, and while merging we increase their rank by 1. So their rank is 1. After it, when we merge this subset to these 2, we merge less subset with less rank as child to our to another subset. So the 2 becomes the child as of the first. So 3 becomes the child, because the rank of the left subset is 1 and rank of the 3 is 0. I need to show the code, because explanation out loud is not easy. Yeah, union by rank. We find parents. If parents is the same, it means that the elements are already in the same set, and we don't try to add it to each other, to some subset. Then we get their rank of their representatives of each subsets where these items contains, and then we just compare if rank of the first item less that rank of the representative of the first item is less than the second item. Then we set a parent of the right item as the parent of representative element of the right item we set as the parent of our left item. Yes, and this is how left item becomes merges into subset, into one subset of the subset which contains left item, the I, merges with subset which contain the right item, the J. Otherwise, if ranks J rank less than I rank, and else means that ranks is the same. When there is the same, it doesn't matter which subset we should, which subset's representative should become commons representative. So we just take one of them and we increase the rank of the new subset by 1. And that's how it works. Size is the same, but size almost same, but size calculates the height of the of each tree. So where we can see it, we can see it here. Each time when we set representative, this item as representative, sorry, not by size but by amount of items which contains in this subset. Each time when we set JRep as representative for item, we increase the size of JRep, and it doesn't matter when if J's size is less than or equal of to I's size, make J's representative a child of I representative. No. The code is a little bit different because we didn't they didn't because this code is common to case when sizes are equal. So but it was equal with this one. They didn't do it here because the first else, the else if part of a condition, no, not condition, the body of this condition is not the same with one where ranks is the same, but as if doesn't matter to which side we increase it, we could swap irep with jrep here and makes the same. So it basically is the same. If sizes are equal, we increase the rank, but we don't use it. So if here this statement we have have it here only because only to for the case when if we will use the size and the rank both, but I think it is redundant here because we use sizes and it doesn't matter, rank doesn't matter for us. Yeah, it looks like it's just copy pasted here. Oh, anyway, let's move on. Here is the example of find here we have a bit more. Here we have here we had simple structure of items without weights of the graph. We just here we had a graph just with edges, but here we have the weight of each edge, or I'm missing something. Maybe, probably, because I don't see subsets, rank, parent is the same as representative. It is the representative. So we have the structure where we created graph, filled it with an edges, and we have a method where we just check if graph contains any cycles. We create subsets. We create subsets here, all the subsets parent v with 0 ranks. I see, I got it. As I said before, we just create we initiate our structure with subsets, our subsets with the structure when each item is in its own subset. We can see it here. Subsets v parent is v is itself. New subset v itself, and we change its rank. Then we find parent for each. Then we traverse through edges of graph and watch get if its verticals lays in the same subset, If yes, then it means that we have a cycle. I don't get it yet here. How we don't, how it can not, there cannot be in the same subset if there they are in, can be in same subset as, for example, 1 and 2 connected with one edge, and we join. I see. For example, we start with which ones? 0, 1, 0 and 1. Initially, 0 and 1 lays in different subsets. We check it out. This condition is falsy, so we union them in common subset, in one subset. Like this, because initially they have same ranks, and increase it is the details, but okay. We union them, then we take the second edge, 1 and 2, 1 and 2, find their subsets. One will be in the subset with 0 and 1 in one subset, but 2 in different subsets. So this is the false, and we union 1, 2 and 0, 1 and 2 to one subset. And in the last how can you say, iteration, in the last iteration we will find out that 0 and 2 have the same parent, and we will return 1 here if a cycle equals 1. I see now. Okay, it was the theory, it was the review of the theory. I read it before, but it's pretty complicated for me. Now we have the task. We have points. I already read the description as well. So we have an array of points. This array represents coordinates of each point. The cost of connection to points is the distance, but not the distance like which measured like how to say it, not the direct distance which is measured as something like vertical distance to between them squared plus horizontal distance between them squared, and get the square root of result sum. No, it's Manhattan distance. I guess it's to make calculations easier. So we just get the absolute value, the sum of absolute values, the sum of the distances by x and y axes. How can you say it? Along horizontal axis. Not horizontal, but along each axis. Okay. And we need to return the minimum cost to make all points connected. All points are connected if there is exactly one simple path between any 2 points. To solve it, I read the hints. So we need to connect each pair of points with a weighted edge, the weight being the Manhattan distance. So we need to create, I don't know, maybe array of distances between every points. Points length is 1000. All pairs are distinct. Each pair of points, yes. So it will be a huge number, but I hope it is. We have no tests with 1000 items, or it is predicted by them that calculations can be pretty expensive. Go to the hint 2. The problem is now the cost of minimum spanning tree in graph with above edges. Here we go to Kruskal's minimum spanning tree algorithm. What we do in this algorithm, we sort all the edges in non-decreasing order of their weight. So we need to create array of edges. Then we make these 2 steps. Pick the smallest edge, check if it forms a cycle with existing tree, not existing, with the graph which we try to create, this one. If the cycle is not formed, include this edge, else discard it. And repeat step 2 until there are v-1 edges in the spanning tree. So we just create array of edges with these points, maybe not array, maybe something else. Then we go through this array until we will reach and until we will fill in the result array of edges, until the result array length will become equal to points length minus 1, or until the end of the array. No, not until the end. We will get it earlier. We have solution in each case. So let's try. What's first? First, we need to create an array of edges. Var edges fill in create edges from points. Then while no var result, not result, var our graph is empty, while graph. So I write the high level steps of solution, and I'm going to implement details later. While graph length less than points length minus 1, it initially it's less, then when it will become equal to points length minus 1, I should stop. After it, I need to edges. What will be edges? The edges is what is the edges? Edges is 2 points and distance between them. Why do I need points in the edges array? Probably, but for calculations I don't need it. Return get just length graph. If what I need to do, I need to check if graph will have a cycle with var I0 to increase I by 1. So or no, and I less than edges length. Here it is, yes. If, how can I check it? If I need to check if subset of current item is cycle. Graph and edges item is not cycle, sorry, then graph push edge, something like not edge, edges I. Okay, let's start from the end or from is cycle. I guess I need to start from is cycle. Var is cycle is function I need some structure, some example code. Because it is hard to understand Kruskal algorithm. We sort the edge array in ascending order. How we get sorted array. We didn't get it, we just have it. 5 3 each edge is coordinates and distance, or what? Or index of each point and distance, probably. A, B, return. Yes, the last is the distance. Okay. We create parent and rank. Then we create set of parent, rank, and what is make set? Make set is we create it's in init. We init initial structures, parent and rank. We fill it with empty values. Let min cost is 0. Then we start it. We find parent, we get the weight. If there is not equal, we union them. If the parents are different, that means they are in different sets of union. We even don't need to check for cycles. We already know by the parents. Okay. It's easier. I need to copy it or not. Parent, I need two methods, find parent and union. Also I need parent array and rank array. Find parent. Parent component, find parent. Okay. In each edge is it's just indices of each point. So we actually don't need coordinates when we fill edges with points. Okay, how can I use implemented? I have edges, I have parent and rank, and then I initialize them. Min cost. Why I need min cost? We create min cost. No, we don't create, we calculate min cost each time when we add up something. Var min cost is 0. Min cost was equal edges I2. Second item in edges will be the distance, and I just return min cost in the end. What else? Edges, then I need to create var parent new array. How much parents I will have? Same as edges? No. I will have, yes, the same as edges, because I will work with the same as points, because I will put each point to a different subset. New array of the size points length, and it's the same with rank. Points I can do more. I need just get parent rank. Okay. I don't need cycle. Var init is function size init what init subsets doesn't matter. Var parent array size var rank new array of size how we will init it. Yes. For I equals 0 less than size parent of each item itself. Rank of each subset is 0. Then we return parent and rank. No, not init parent and rank. Then what we do, we calculate mean cost, and we don't need graph in our main code. Var get mean cost is function which will do this thing. Graph mean cost I need parents, rank arrays, and size. Parent rank, also I have edges. Here I make find for each of the item. Var I rep find parent, find parent, find what will find find edges I 0 and parent and rank. Var j rep edges I1 parent rank. I don't like I and J. Let's name them like I don't know, first and second. First point and second point. Let's name them point 1 and point 2. And then if point 1 does not equal point 2, we push to result it doesn't matter what we push. We push something. We even don't need this array. Then we increase this. Okay. Now I need to write the find method. Find function. What I pass to find. I pass here the index, the parent, and the rank arrays. If parent I equals I, return I. Else return parent parent what? Find parent I. Yes. I don't need rank here. I need rank here when I will union get min cost, return get min cost, edges parent rank and size, edges parent rank and points length, and I don't need any of it. The main code is looks pretty simple. I like it. I create initial subsets. I create edges. Yeah. Union. I make union of this point and this point inside of parent array and using rank, using rank their ranks. So var union is function let's say ij parent and rank. So here we know that ij is not in the same subset. If so, we just rank I less than rank j. What we make if something's rank is lesser, then we put here under the something bigger, and we don't change ranks. So we make parent of I equals to parent of j, or we make it as j. I don't remember. I will check it. Let me write it. If rank I more than greater than rank j, then we do it in other sides. Else it doesn't matter. We make the same code. We can do it like this. Else also if rank I equals to rank j, we increase rank I as of I now has more children, we increase its rank by 1. Let's check, am I right or wrong? We find parents, we get weight, we increase weight, mean cost by weight, we union items. Why we have n here, I don't know. If rank lesser, yes. If rank of the first item is bigger, here is misspell. It should be v and u here. And we may set parent u and we increase u's rank. The end is redundant here. Looks like that is all. That's it. Let parent, let rank. Probably no. I can do not check this condition because when I will get this state, I cannot make any other connection, but I will leave it to prevent redundant iterations in my cycle, because when I reach this state, I don't need to check other edges. Also I do need create edges method, and their edges should be sorry they should be sorted. Points var result is empty, return result. Probably it will be hardest, but no, it is not the hardest. We just go through our array. I need to go through array var I equals 0, I less than length. How can I is it possible to add edges and let them be sortable? Don't know. Looks like no. I plus equal 1. So to get every combination of pairs, I need to iterate one inside other. I need inner loop j less than points length j plus 1. Also j should be equal to I plus 1, and I don't need to go until the end to prevent duplicates. So if points length what we have, if points length equals 1, if points length equals 1, return 0. If points length equals 2, return get distance points 0, points 1, and that's it. And starting from here, we have limitation points return what we return, number like that. and I need comment like that. Points length more than 2. So we don't need to check it here. So if points length more than 2, then we can do things like that. Yes. I equals 0, length is 2, I less than 2 minus 1 is 1, j equals to I plus 1. It's 3 at least. J equals to 1 plus I plus 1 plus 1. So it is 1. 1 is less than 3. Looks like we can feel it. Also we need to sort it out. Result sort. Point 1, point 2. Not the point. Edge 1, edge 2. Return edge 1 distance minus edge 2 distance, and we return sorted edges array. Here I need get distance method. Function distance between 2 points, point 1, point 2, point return point 1 math apps point 1 0 minus point 2 0 plus math apps point 1 1 minus point 2 1, and that's it. Here we push result push. What we push? I in J, and get distance points I, points J. And that's it. It's pretty big amount of code. Probably I forgot something. Reading 1. Cannot read properties of undefined, line 38. Function I parent find, where I invoke find. Where I fill in parent and rank here. So let's watch what is in parent. Parent is okay. We have values and ranks. Why? What do you mean reading? Aha. Problem is in here. Parent. I forgot to pass the parent array. Wow. Oh. Huh. It works from first time. But it doesn't work when I submit it. Only 8 of 72 test cases passed. Well, I have 5. I have five somethings. Let's watch what is in the edges. Use test case. I don't want to submit it anytime. Edges. 0, 1, 2, 3, 4, 5. 3, 5. Distance between them is 12. Aha, why my distances is not sorted? No, they are sorted. What I'm missing? What I am missing? Let's console log something else. Let's console log result graph. Result graph, main cost. Let's graph and result parent and rank. Three, 5, 4, 5, 1, 3, 0, 3, 0, 4. I connected 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. No. 0, 1, 2. I didn't connect the 0. I didn't connect the zeros. The second point. Point with index of 2. Where it is? Here it is. Or here. Probably I need to connect it connected. I guess my code works wrong somewhere. Where? So we have one subset of 4. So first point is one subset with 0, 1, 2, 3, 4 with fourth point. Fifth and fourth as well. Fifth, fourth, zeros. Yeah, here it is. Here them. Then the second is in the separated subset and it didn't connect it. And third and first indices is in the same. First, yes, here it is. And where is here? Why zeros? I have a cycle here because fourth connected with fifth, fifth with the third, third with the 0, and it come back to the fourth. Let's try to prove it. So I need 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 4, and 5. Let's watch how they're connected to each other in my keys. 3 and 5. 3 and 5. Then 4 and 5. Then 1 and 3. 1 and 3. 0 and 3. Oops. 0 and 3. Then 0 and 4. And here is the cycle. My code works wrong. In the last case, it should understand that 0 and 4. Why is last? Aha, first, second, third, fourth, fifth. Yeah, it's okay. When it tried to add it here, it should when it check it, it don't make cycle yet. So 0 and 4 at the moment of checking is not in the same subset with 3 and 5, for example. No, it's in the same. But what is... I don't understand. 3 and 5. You check 3 and 5. Their parents are different. Let me do this one. after let's console log it after each iteration. Initial iteration, we see initial iteration and we see each iteration. So it will be 0, 1, 2, 3, etc. Let's run it and analyze it. So first one, we put 3, 5, 12 edge and we made 3 as a parent of 5. Okay, and 0, 1, 2, 3. 3 increased its rank. Okay, let's take 4 and 5. And here is problem. My code of changing parents is broken because I made the 4 as the parent of 5. 3 was the parent of 5 and changing parent while finding parent is wrong. Parent component equal component, return component. Return parent component. I need to, I see, I need to reassign parent, recalculate it. Each time when I make find let's write parent I equals to this parent component, yes. Let's run it. Now it should work. It doesn't work. Why it doesn't work? Let's watch the result. Parent I sorry, it is some magic. Parent I equals find it parent, so we reassigned it and we return reassigned value. If it is I, parent I, parent I. Wow, why it doesn't work? Actually, I don't need return here. Let's make it more clear. Parent I. If we find parent I, we return it. If not, we search for its parent, for items parent, because for parent of this parent. we search for parent of I element of. If the element itself is parent, we return its element. If not, we search the parent of its parent. Yes. We search the parent of its parent. And when we find it, we reassign it. If it is changes, why would it change? It change when we make union. Aha, here is my problem. When I make union, I need to find parent before yes, I need to compare ranks of the parent, not of the parent itself, not of the rank of the item itself. So var I rank is no. Equal var, sorry, no. We find items. They are the parents itself. Then, if they are not equal, we union them, not the current items, but their parents. Yeah. I even can't copy it right. So, and here I don't need to find parents because they're already parents. Oh my god. Work, please. Whew. Submit. Output limit exceeded. Oh my god. Sorry, where is my console logs? Where is my console logs? No more console logs. Accepted. Wow. Wow. It was hard one. But I'm glad it is successful for me, even though I copied some code, but it is a medium level problem, and I solved it. I how to say it? I believe that I made it in right way as for studying because I read the theory, I learn it, I research it, I learn it, how to say, deep, not just read it, but I try to understand each what made each line. It wasn't perfect, but I made I made maximum of me to it. I learned new things, and I see the results here. The numbers is not important, but it is sorry. It's very nice. It's very nice when you see the green numbers. I don't know, more than 50%. I don't tell about 90, but even green numbers is okay, especially when you spend a lot of time and you make a lot of efforts to finish it. Well, now it's time to watch other guys' solutions. I tried to watch. I watched the size. I watched the size of solution before starting, because it's pretty big. I can reduce it, but I will not, because it was not easy. Yeah, you see, my God. He made it with he made MST too. MST is minimum spanning tree, but I guess he didn't take right approach creating MST. Points are only given to calculate the distance. We can create a heap which will store the minimum distance and nodes having that distance. After creating this heap, we need to pop the minimum node, i.e. root, and check if it's not making a cycle. And that node, add that node, else skip. We will pop until we have n-1 edges, where n is the total number of nodes. Let's start from the end. Find MST cost. Min cost connect points. He created heap. What he do? He fill in the distances for each point. For each point he fill, for each point he fill in distance between distance to each other points. How he skipped the same points. Aha, I plus 1. So he don't make duplicates where the distance to point itself is 0. Node with distance ij. Okay. Find MST coast. Min heap points length. Min heap prototype push function node. Prototype delete. Aha, he was created and he made the methods to add and delete items from heap. Push node, this heap push node, index heap length -1, parent math floor. What means IDX? Index of last item. While parent, what is the parent? Parent is my middle element. What? I don't know. I don't understand. Okay. Parent more than equals 0. This heap index 0 less than this heap parent 0. Let's swap. Yeah, I guess I understand this approach in common, but it looks overcomplicated after I get this Kruskal minimum spanning tree algorithm. Okay, what it is? This heap, let's swap this heap parent. Oh, parent swap. He swapped the items until what? Until the first until the last item in heap. Yeah, until last item in heap is less than middle item in heap. Okay, then he move pointer of ein index to parent. It is the middle of the heap, and move parent pointer to quarter of the heap. I don't understand. Let's just leave it. Find MST coast. Let connected nodes coast is cyclic. Oh my god, no. I'm not ready to understand it. Here is about Manhattan distance, etc. Here is Java. Where is the Python code here in JavaScript? it is Go, it is Rust, it is C, Java, not JavaScript, C Sharp, PHP. Okay, let's watch Java solution. Aha, he solved it with priority queue. If someone remember, JavaScript doesn't have built-in priority queue. So this is the reason why priority queue, with solution with priority queue will be more will be bigger. We'll have, I don't know, some 20 or 30 additional lines of code, maybe 40. Let's watch the Java. Manhattan distance. We have points, visited, hash map, priority queue, min heap. It is with heap again, while min heap is not empty. Min heap poll. If visited or the continue, I don't understand. Oh, no, I'm not ready. Aha, Prim's algorithm employs a priority queue, and Kruskal algorithm uses union find. Aha, I didn't read Prim's algorithm because Kruskal's goes first. Well, I need to learn Prim's algorithm. Where is the priority queue? I don't see it. I don't see it. I don't see it. Aha. He made the Prim algorithm. Is the Kruskal? Kruskal. Approach 1. Please. Kruskal algorithm. Yeah, find, union, the same. Kruskal. Blah, blah, blah. Find parents, union, sum. Aha. It doesn't have additional graph. I see. Okay, it's too long. I'm tired. I need to stop. I don't, my brain doesn't work. Thanks everyone, and bye. Thanks everyone for watching again.